All right, hello everyone. I'm Greg. I'm from the Pawsey Supercomputing Research Centre. I lead the team who manage our Ceph object storage clusters, and I'm here at my first Cephalicon, very happy to be here. And I'm here to talk about how we've designed our new 20 petabyte Ceph cluster for object storage to be resilient, performant, and cost effective, while also paying attention to recommendations from the community. Pawsey is one of two Tier 1 high-performance computing centres in Australia. Our work is to provide supercomputing, data, cloud and visualisation services to support research across a spread of scientific domains. This all runs on, I've got one more slide there. This all runs on equipment in our data centre in Perth, Western Australia. I mentioned recommendations from the community a minute ago, and I want to clarify that I mean a number of sources. I won't read them all out, but the sources of advice and leads on where to search are invaluable, and I will make special note of two of them. The upstream main documentation has a raft of information on getting started, deployment, configuring, troubleshooting, and I now hear there's a new beginner's guide, so I'm looking forward to reading that. It's helpfully published with a version in the URL because we don't run the latest version, so it's easy to switch between versions. The Red Hat and IBM docs are also good for finding information and procedures to augment the main docs. In recent years, Pawsey has successfully shifted from mostly using cluster file systems to a central object storage system, with Ceph as a key component. We're continuing this system by adding a new cluster for NWA, which is a radio telescope project related to the SKA. On the left, you'll see the key equipment specs. The bulk of it is in what we call storage units, composed of 60 22 terabyte drives in a JBOD chassis attached to a head node. Sorry, I've lost my place. Before looking at more details, I want to note that we have well-established requirements for this cluster and a strong working relationship with its users. This helped us design it to meet requirements from now and into the future without having to over-engineer it. We've deployed a number of Ceph clusters with HDDs as the main storage over the years, and while all specs are important, we're always concerned about CPUs. We've been careful to ensure enough CPU capacity, and vendors have generally encouraged us to have ever more CPU intensity. But in practice, we've found that regardless of whether we use replication or erasure coding, we find the CPUs on the OSD nodes to be very quiet. So with each successive new cluster, we've dropped the CPU intensity, and we've done this again with the newest cluster. It has 64 cores for each storage unit, and this time that also includes all of the other co-located daemons. It's not yet clear that the production workload will be perfectly aligned to that, but Ceph ADM makes it easier than ever before to move daemons to different hosts. Pawsey has a 400 gigabit backbone, 400 gigabit network backbone, and a standard of 100 gigabit links to all new equipment. For this cluster, we're using cheaper Broadcom NICs instead of the usual ConnectX series. We have yet to see Ceph saturate any of our links though, so we still expect to see good performance. And this is proven out in benchmarking so far. You may have noticed that these storage units are quite large, with over a petabyte of raw capacity on each one. We fully expect that in the event of a complete node failure, rebuilds will take many days. And even more concerning is that it will reduce cluster capacity until repairs are done. This isn't acceptable, so our plan is to use only 24 of our 26 available storage units, keeping aside 2 for testing purposes, but available when we need them. We've long deployed Ceph using Puppet and Ceph Volume, which has included KVM virtual machines, which cost RAM and CPU to run, as well as network overheads. We're making the leap to learning Ceph ADM, and while it hasn't all been plain sailing, it has some strong advantages, including the containers using resources better. The final piece is the index nodes. The cluster is for Rados Gateway, which requires a high-performance index pool. Fortunately, the size of this pool is a mere fraction of the main data pool, so I can be satisfied with only 4 nodes. Moving on to how to design the cluster, the challenge is to determine and communicate requirements. If possible, get them directly from your users, or at least characterize their usage. You might need to work with fast enough to do our work and up most of the time, or you might get performance, capacity, and availability described in detailed numbers, which will give you more accuracy. As I'm sure it says on the glossy brochure, Ceph's resilience is legendary. It can also provide very high throughput and lots of IOPS. And it can also be very cost effective, but it can't be everything everywhere all at once. So, do you have a budget? Are you experimenting with existing equipment? This is a very good idea to get a sense of what you're working with, but you need to have enough to get a decent proof of concept. Next, who are your users? What is their appetite for performance and for outage and, frankly, for cost? Do you have requirements to meet at the best possible price, or a fixed budget to buy the best possible cluster? For example, we had a fixed budget and a rough sense of requirements early on for capacity and performance, and we also knew that this cluster can afford to be offline for planned periods. Those all feed into how we design it. There's a range of ways to operate Ceph. You can run it entirely yourself, which means you will dive into the deep end of all deployment and operations and learn a lot along the way. You will need to establish skills and procedures for the relevant tasks and decide who will be responsible for the design work, for the day-to-day operations, and for what happens when things go wrong. You can also run it yourself and pay for some support. For example, you might operate and troubleshoot your own clusters, but have a paid arrangement for support with designs. The companies offering these services each offer slightly different arrangements, so it requires a bit of time and work to talk to them and decide what suits you best. In fact, you might start that this week because there's a whole lot of people on site and in-person conversations can be pretty rewarding. There is a third option to consider, and that's going all the way to a managed solution. If you have operational funding which grows with your storage capacity, a managed solution might suit you well. And of course, those same companies will happily talk to you about that. I also suspect it would be possible to run Ceph as a software as a service model directly on something like public cloud. I've got a sense from talking to some people today that it's possible. I don't know if there's any packaged solutions out there. Bear in mind, though, that the community is always there, regardless of which approach you use. Of course, the more things you run yourself, the more responsibility that you and your team will hold, but asking questions is free, and responses to other people's questions on the various forums can be very helpful. I encourage you to provide feedback when something does prove to be helpful, and to share the knowledge you do have, even if you don't feel like an expert. I know I don't, but it feels good to have helped someone, even in a small way. Automation can be helpful in operating a cluster, and it can be seen as a continuum. Early on, you might be stumbling around with manual commands, ad hoc semi-procedures and scratchings on bits of paper. And the first step from there is to write down what you do. Then you might write some scripts to automate some of it and share some of those scripts with colleagues and start putting it in repositories and other, more sophisticated systems. From there, you can build or find automated tools to deploy everything and manage everything for you. But be aware that all code must be maintained, and understanding the code is also useful for troubleshooting. That is important when team makeup changes, so look after your documentation and your induction procedures. Turning back to cluster design, you can think about failure conditions. Do some thought experiments, or better yet, some actual experiments with a test cluster on what happens when certain equipment fails, or when someone puts in the wrong setting, or when the default route for Ceph monitors is not working or gets deleted. Many settings can be changed in a live cluster, but the best time to decide on your overall architecture is before it's deployed to production. Consider the most likely failures. For example, don't spend all of your money optimizing power redundancy if you're using wet string for networking. Larger Ceph clusters with many nodes are fantastic for scaling out performance and resilience. Do pause, though, to consider adding a new cluster. Running multiple clusters increases administrative overhead, but there are benefits too. When problems arise, and you not only have another one to use, but you also have a live reference point for what is working, which can itself help with troubleshooting. So large, dense clusters full of HDDs can be effective if they match the user requirements and have suitable understanding and support. There are many ways to successfully deploy and operate a cluster, and as you just explore them, you'll find the best path for your situation. Thank you.